Hi, and welcome back to Algebra 1B. Today we're going to be discussing our final lesson, comparing linear, quadratic, and exponential functions. And to do that, we've talked about all three of these before. We've talked about what their equations, tables, and graphs look like in our last unit. We've discussed how to create those equations in the units before that. So in this unit, we're actually going to be comparing them and comparing the growth of them. So let's start that by actually looking at some problems. So let's talk about Mr. Wiggins here. Mr. Wiggins gives his daughter two choices of payments. Method 1, she can get $2 for each bag of leaves that she fills. Or option 2, she will be paid for the number of bags of leaves she raked as the following. First bag, she gets 2 cents, 4 cents for the next one, 8 cents for the next one, 16, 32. You can see with the amount doubling each additional bag filled. Then we have a couple questions to ask ourselves. If Celia rakes enough to fill 5 bags of leaves, should she opt for payment method 1 or 2? What if she fills 10 bags? And how many bags would Celia have to fill before method 2 pays more than method 1? So that's what we're going to work on today. So go ahead, take a moment, pause the recording. See if you can come up with equations for these two methods so that we can figure out what kind of equations those are. And as you're coming up with them, think about it. Are they linear, quadratic, or exponential? And create the equation. Alright, hopefully you've had some time to pause here and come up with the equations. Our first option here, $2 for each bag of leaves. $2 for each. That tends to tell us it's going to be a linear equation, and hopefully you're able to come up with the equation as 2x, or 2 times however many bags of leaves, whatever variables you use. That would be the equation for the first one. The second one may be a little bit more difficult to come up with. It is doubling each time. Hopefully that gave you a hint that it is an exponential equation. Remember we talked about that in the last unit. Has a common ratio going from one to the other. We know the common ratio is doubling. So our ratio, common ratio, or B, is 2. And we need to know our initial amount. Well, for one bag, we get 2 cents. Our initial amount would be for 0 bags, if we think about it that way, because we want to know A sub 0, or that where it's crossing that y-intercept. So we can find that by dividing by 2 cents by 2, and we would get 1 cent. So 0.01. That's my initial value. And then if you need that equation, remember the standard equation for an exponential function. AB to the x power, where A is our initial value, B is our rate of change. Our standard equation for a linear, y equals mx plus b, where m is our slope, b is our y-intercept. Alright, so now that we have our two equations, if Celia rakes enough for 5 bags of leaves, should she opt for payment method 1 or 2? Well, let's go the easy route and look at the graph. So take a moment, feel free to pause it right now and graph it on Desmos. We love Desmos. Alright, so hopefully you had a chance to graph it on Desmos. Again, pause the recording if you need to. Here is what it looks like. Method 1, y equals 2x. That is my red line, my nice linear equation. Method 2 is the blue line. That is my nice exponential equation. And remember, The first question was, if Celia rakes enough for 5 bags of leaves, should she opt for payment method 1 or 2? So let's look at where 5 is. X is the number of leaves, bags of leaves, so 5 would be about right here. And if we look at 5, she definitely is going to get paid a lot more for method 1. Method 2 is looks like not even $1 yet. So 5 bags of leaves, she should go for method 1. Method 1. What about 10 bags of leaves? So look where X is 10. Which one would give her a better pay? If we look at 10 here, you can see the blue one is quickly approaching, but it's still less than, it's right at about $10, still less than method 1. So she's going to do 10 bags, she should go for method 1. But if we look at our last question here, our next question, how many bags of leaves would Celia have to fill before method 2 would pay more than method 1? Well, if we look at our graph here, I highlighted the point right here. If she filled 11.12, or we can round up and say once she fills that 12th bag, method 2 is going to pay more than method 1, and you can see the amount is very quickly increasing. That is one of the things with exponential functions is it may be a little bit slow in the beginning to rise, but once it gets going, once it starts really increasing, it increases much faster than the linear functions. So Celia, how many bags of leaves would she need to fill before method 2 pays more than method 1? Our answer was 12. At 11 bags, it was still a little bit less. When you reach that 12th bag, she will get paid more with method 2. All right, let's look at another example here. Population and food supply. The population of a country is initially 2 million people, and it's increasing at 4% per year. The country's annual food supply is initially adequate for 4 million people, and it's increasing at a constant rate adequate for an additional 0.5 million people per year. Based on these assumptions, and we have a couple questions to answer. So, let's take a moment here and examine this again. Can we actually create some equations that model each situation? One situation being the population, and one equation being the food supply. So take a moment, pause the recording, and come up with equations that model the population and a separate one that models the food supply. All right, hopefully you've had a good chance to get those equations down. Let's look at it here to make sure we all have the correct equation. Let's look at the population first. The population of a country is initially 2 million. It is increasing at 4% per year. Anytime we have something increasing at a percentage, that's increasing by a common ratio. So that tells us this is going to be an exponential equation. We've got our initial amount of 2 million. I'm just going to write that as 2. I'll just have to remember that's millions we're talking about. And it's increasing at 4% per year. So my rate is going to be 1 plus 4%, or 1.04 as my rate of increasing. And that's raised to the x power. Again, using my standard exponential equation, y equals abx. Y equals ab raised to the x power. That's better. Where a is our initial, 2 is my initial, and b is rate of change. So my rate of change again was 1 plus 0.04, since it's increasing 4% per year, or 1.04. Alright, so now let's look at the food supply. The country's annual food supply is initially adequate at 4 million per people, and is increasing at a constant rate, adequate for an additional 0.5 million people per year. That constant rate, that tells us that we have a linear equation. Remember, usually when we see that per, the number before it is going to be our slope. So 0.5 is increasing per year, plus our initial 4 million. So these are our two equations. You can see again we have one that's exponential and one that is linear. Alright, now that we've got the equations, if we were to graph those using our best friend Desmos, based on these assumptions, in approximately what year will this country's first experience shortages of food? So if we look at our graph, our red line here is discussing or showing us population. Blue is the food supply. So if we want to know in approximately what year will this country first experience shortages of food, it's going to be right here where the lines cross. Because initially we've got enough food for the population, but as our exponential equations usually do, it starts increasing rather quickly. So you can see it's just below 80 years when the first shortage of food will occur. If the country doubled its initial food supply and maintained a constant rate of increase in the supply adequate for that 0.5 million people per year, would shortages still occur? So think about it. Come up with a new equation here. If the country doubled its initial food supply, so we're doubling it, it was originally 4, now we're going to double it. Would I still have a shortage? Or would this country still have a shortage? So take a moment, come up with the equation. Again, pause the recording so you can come up with your equation. Alright, hopefully you've had a chance to pause the recording. Your new equation here, we are still at 0.5 per year. It's increasing, but my initial amount was doubled. It was originally 4. Now it is 8. Alright, so our question is, would shortages still occur? And if so, in approximately which year? So again, take a moment to graph this and determine, compare it again to that last food graph we had. And here is what you would get. So you can see, once again, it will still have a shortage of food. A little bit later than before. Remember, it's a little bit before 80 years the last time. Since we doubled our initial amount of food, it's buying us a little bit more time, but it's still right around 82 years, 81.4. The food supply will run out. So doubling our initial amount didn't help. What if they also doubled the rate at which the food supply increases? Remember, originally, our food supply increased at 0.5 per year. So let's double that. So 0.5